Okay, hello everyone. This is a remake video to the example 10.8. Okay, and the reason why I remake this video because I want to correct some sign convention issue for the torsional loading problem. And the example T and 10.8 is a statically indeterminate problem. Actually, this problem is very similar to our introduction problem for statically indeterminate torsional load problem. Okay, so that's very similar design. Okay, we have a shaft fixed in the wall. We have shaft and stuck and fixed in the wall in the two wall. Okay, and we apply a two torque under this shaft. Okay, the problem want us, okay, find the reaction torque at the position A and position B. Okay, the problem is what is reaction torque at A and reaction torque at B. Okay, and for such problem, yeah, first of all, we also need to use the rigid body equilibrium to write down the overall equation. Okay, because everything is statics in this problem. Okay, so for statics, so the overall torque is equal to 0. Okay, so yeah, there's a torque at the position A and position B, but the problem, maybe a lot of people has problem, what direction should I assume? What direction of torque A or what direction of torque B should I assume? Actually, in the last video, introduction video, I said you can assume any direction you want. TA, TB direction. What's the direction? Okay, you can assume anything. You can assume any direction you want. You can assume any direction you want. Okay, but last video I said, but you have to design, you have to define which one is positive or which one is negative. Okay, for example, in this graph, he assumed TA is rotate in this way. Okay, TB rotate in this way. Okay, and now I assume this way is positive. Okay, let's use this we define this positive sign. Okay, rotating this way is positive. Okay, let's write down the rigid body equilibrium. Okay, because I define this rotating in this way is a positive, so the sign of TB is positive. And the next one, the torque 800 Newton times meter. This torque, okay, what's the direction on? Okay, the direction is this, so it's reverse, it's opposite to the TB. So I define this way is positive, so that's why the sign of this 800 torque, the sign is negative. Okay, so it's 800, 9 minus 800. And the 500, its direction is, it's rotated in this way. Okay, rotated this way. It's rotating in this way, so we define this rotation is positive. This direction is positive, so it's 500. And the TA, we assume it's this direction, and I define this direction is positive. Okay, so after all, we will have the TB plus TA is 300. Okay, TB plus TA is 300. Okay. Okay, so when we use the rigid body equilibrium, we only got this equation, but we have two unknown, and one equation, two unknown. It's not impossible to solve this problem. So we need to find another equation from the system. So I call it constraint. What's the constraint of the system? What's the constraint? Okay, constraint of the system. The constraint is phi. Okay, angle of twist B, B to A is 0. B to A is 0. That means because this wall is so rigid. Okay, so angle of twist relative to these two positions must be 0. No matter you look B from A, if you stand at point B, you stand at point B to look the angle of twist of A must be 0, or you stand at A, look at the angle of twist of B, it must be 0. Okay, because the wall is so rigid. Okay, so it won't have any angle of twist, no matter you stand on point A to look at B or stand at point A to look at B. The angle of twist must be zero. Okay, that's the constraint of the system. But okay, but and in this problem we also have many section because there's a torque at position C and torque at angle sorry, there's also a torque at position D. So this system we have is three section. Okay, we have three section. Three section. Let me draw. We have these three section. This one, this one, this one. We have BC section. We have a CD section and a DA section. Okay. Okay. The overall angle of twist must be zero. But since we have these three section, okay, so actually this angle of twist of the whole system can be decomposed into these three parts. Okay, it's right in the equation means okay the total is B A is equal to angle of twist B look at C plus C look at D plus D look at A. Okay. Okay, I think that's the most important part of this problem. When the angle of twist from B to A is equal to the linear combination of these three sections. Linear combination of these three sections. Okay, you have to use your imagination to understand this. Okay, yeah. Sorry, I don't have real object to demonstrate this problem. So, but you have to use your imagination. Okay, but I think I will find some time to find some. I will make another graph, but because right now I use the control pen and use the panel, I cannot write a very beautiful graph. Okay, I'll use my another time to draw to explain this concept. Okay, so then for this video, let me just finish the calculation. Okay, so we need so this add together must be zero. Okay, okay, so this is our constraint. Our constraint is here. With this equation and TB plus TA is equal to 300, we can solve the problem. Okay, so how to calculate the angle of twist in BC section. And for the angle of twist, don't forget our formula. The angle of twist, the formula is equal to T L over JG. Okay, T is the torque, L is the length, J is polar moment of inertia, G is the shear modulus of this shear modulus. What's the shear modulus of this problem? The problem didn't give us the shear modulus problem, but maybe that's we don't need it. Okay, so write down this equation. So it's also TBC times LBC divided by G and J and plus TCD times LCD GJ and plus T T T T T T T T T well TDA and LDA and GJ and add them together equal to 0. Okay. To 0. Okay, so because this is on the same material, okay, it's the whole shape is same material and the same cross-section area, so everyone has the same G times J. So we can multiply G times J on both sides of the equation, so we will have the TBC times LBC plus TCD times LCD plus TDA times the LDA equal to 0. Okay, and do we know the length information? Yes, we know it. Okay, we know it. Okay, we know 0. LBC 0.2, so 0.2 TBC plus LCD is 1.5 TCD plus 0.3 TDA equal to 0. Okay, So, okay, we have the equation for TBC, TCD, and TDA, but our rigid body equilibrium equation is TB plus TA. It looks like it's different, but we can use cut section to link these two equations together. Okay, okay, like I say, what I said, we have three section in this problem. So let me cut the three section. Okay, so let me draw the cut section graph. This here is okay. Here is another one. And there's the final one. Okay, we assume there is a TB here. Is TB. Here is TB. Yeah, let me cancel this. Okay, so here is in BC section, here is a TBC. So what direction should I assume for TBC? This way or this way? This way? TBC this way? Okay, TBC, we assume TBC rotate in this way, and then right here we need to use the sign convention of torsional law. Okay, TBC, I assume it rotate in this direction. Use the right hand rule. Okay, its direction is point outward to the surface. Okay. Okay, here we'll have a TCD. So it's rotate in this direction using your right hand rule. It points outward to the surface. That means positive. And rotate in this way. Rotate here is TDA. Okay, it's rotate in this way, so it's also positive. Okay, so use a right hand rule. Okay, let me write down the other torque. The torque here, yeah, the section here sorry. Here we have 800, and here is 800, and here is 500. Okay, for each section, we have to use the rigid body equilibrium to analyze these three cut sections. Okay, because everything is static in this problem. So the total torque on these sections must be 0. Okay, so I don't have space here, so maybe I have to clean this. Okay, so I think we don't need that. Okay, so okay, so let's do the analyze for each section. Okay. Okay, for the first section here, let me say this is section 1, section 2, and section 3. Okay, for the section 1, okay, the torque B here, what's the sign for the TB? Okay, here you need to use the sign convention. It's rotated, use right hand rule. It's rotated in this way. Your thumb direction is here. This is your thumb direction. So the thumb direction is outward to the surface. The thumb direction is outward to the surface. So that means the sign of the TB is positive, and TBC is positive. Okay, it's equal to 0. Let's tell you TBC is equal to minus TB. Okay, the section 2. Okay, the sign of TB is positive. Okay, what's the sign for the 800? Okay, the sign of 800 use the right hand rule. Okay, the thumb direction is in this way. Okay, this is a thumb direction. The thumb direction is inward to the surface. Our surface now is here. Our surface is here. So this direction is inward to the surface. So the sign for 800 is minus. And the TCD is positive. Okay, so we will have we get the TCD is equal to 800 minus TB. Okay, the section 3. Okay, here the TB thumb direction is here, 800 thumb direction is here, and 500 where the thumb direction. Don't forget the right hand rule. Sorry, right. Sorry, this is wrong. Wrong. This direction. And the 500 use right hand rule, the thumb direction is in this way. So the sign for the 500 is positive. So it's TB minus 830 plus 500 and plus TDA is equal to 0. So what you get the TDA is equal to TDA equal to what's the value is 300 minus TB. Okay, so you see TBC, TCD, and TDA all relate to TB. TB. So you just got the TBC, replace TBC as minus TB. TCD as 800 replaced by 800 minus TB. TDA replaced by 300 minus TB. So this is overall you will have yeah, I think yeah, okay, should I write down this equation? Yeah, I don't have any space. Where should I write this space? Okay, where should I write this equation? I don't want to cut this off. Okay, okay, so let me write the equation here. Okay, so I have to erase this part out. Okay, sorry. The comparativity equation, I have to remove this. So we just put the result of the cross section method. Okay, so it's 0.2 TBC is equal to minus TB, and TCD is equal to 800 minus TB, and the TDA is 0.3 300 minus TB, and totally is equal to 0. You see this, by using this equation, we can solve the TB, right? So what this equation tell you that minus 2 TB. Yeah, let me check. Yeah, minus 2 TB, and plus this is plus 1200, and plus did I read it right? Plus, okay, it's plus 900. Ooh, 900. Oh, sorry. So it's 9 to 0. So you obtain a TB is equal to 645 Newton times per meter. Okay. So, and using this equation, by using this equation, okay, with the rigid body equilibrium, you will get TA. TA is equal to minus 345 Newton times per meter. Okay. Okay, so we got this equation. We got we got TB and TA. But you see, it looks like it's not equal to the answer on the PowerPoint. But I think the answer for the PowerPoint means very important information is called direction. Okay, so the sign is because of the direction. Okay, let's look at our initial assumption. Okay, our initial assumption is TB rotating in this way, TB rotating in this direction, and you get a positive answer. That means it's important. That means it's really rotating in this way. Okay, at the beginning we assume TB rotate in this direction, and we get the positive positive answer. That means it's really rotate in this direction. Okay, and then we initially will assume TA in rotates in this direction, but we get a negative value. So that means the TA is rotate in this direction. So the positive and negative, sometimes you have to consider which help consider what does it really mean. It's in rotating direction. Okay, so the problem here, sorry, so for the answer here, yeah, maybe, yeah, you will see this answer is positive 345 and TB is minus 636 minus 645. Okay, I think this is because initial assumption is important. I think what I think is, okay, this answer, it's assumed this one is positive at the beginning. I, okay, at the beginning of this calculation, I think this answer is because at the beginning he assumed this direction is positive. This direction is positive, but don't forget, in this video, we assume this direction is positive. Okay, that's why we will obtain a reverse answer compared to this one. So the difference is because your initial assumption for the sign convention. Okay, so when you in a torsional load problem, your initial assumption is will influence your answer, your final answer, especially direction. But the conclusion is the same. The conclusion is the same. Okay, the conclusion is TB is rotates in this direction, and TA rotates in this direction. Okay, and this conclusion is the same as this answer, because this answer is assume this direction is positive at the beginning. So that means TA is for this answer. Under this assumption, the TA is rotated in this way, and TB is rotated this way. If you look at this is the same. What is the same as what we get here? Okay, so the conclusion is the same, but you will see the answer has the answer looks like the answer is reversed. The answer looks like they are reversed and opposite, but actually their conclusion is the same. The conclusion is the same. TA rotated in this direction, TB rotated in this direction. Okay, so that's why I want to address it in this video, because the sign conventional issue, yeah, sometimes it's drive everyone crazy. Okay, okay, so you have to think about this when you do the calculation and in the practice. Yeah, the conclusion is the same. The conclusion is the same. No matter what sign convention you are using at the beginning, okay, the conclusion it must be the same. Okay, so I just start the video here, and we'll see you in another video. Okay, bye bye. Okay, hope we. It's very very annoying.